Hey everyone, we're going to go ahead and start into the fifth video. I know we got a long way to go with this information, and my goal is to get as much of it in as we can to make sure that you're as prepared as possible for the AP exam. So let's go ahead and jump into it. And our goal is to look at the properties of salts and how they're actually going to affect the pH and pOH of our solutions. Our goal, of course, to get you to that 3.0. But my hope is that you'll be able to look at some of the properties and then make decisions based on that. Now, what are salts? Salts are ionic compounds that are usually dissolved into ions when put in water. Now, when they're put into water, they can behave as either acids or bases based on the information that some of which we've covered and some that we're going to add to it. Now, the salt of a strong acid or a strong base gives a neutral solution. So when we see KCl, NaCl, all those different things, or 18O3, the salt or the anion in those cases, when they're dropped in the water, they're going to actually be neutral. So they're not going to affect the pH at all. A basic solution, the anion for the salt is a conjugate base of a weak acid. So this means that it's actually kind of fairly strong. Now, knowing this piece of information, we usually use our Kb when we start with a base. I'm going to draw your attention here because if we have, say, the Kb value, we can find the Ka value, or vice versa. Now, why is that important? Because we know that this always has to equal out to 1.0 times 10 to the negative 14. We're going to use that information to determine the Kb value for a couple of questions just coming up in a second. So, again, basic solution is formed when the anion of the salt is a conjugate base of a weak acid. So, like our acetate ion, our fluoride ion, if those are added into the solution, it becomes more basic. And an acidic solution is formed when the cation from a salt is a conjugate acid of a weak base. Looking at what we have here, we're actually going to be looking at the fact that we're getting this, which is going to form the ammonium ion in solution. Is going to make it slightly acidic. If we start off with an acid, then that means we're going to be using the Ka value. Now, just as a little bit of a overview that you can look at, the cation is neutral, the anion is neutral, most likely the salt is neutral, which means we're dealing with something like NaCl, something very simple like that. Now, if we're looking at the fact that we have a neutral cation with a conjugate base of a weak acid like sodium fluoride, that means the solution is going to be basic as a result of adding it to it, and it gives the example there. Conjugate acid of a weak base, we're looking at NH4, and the neutral anion is going to be acidic, and then we go from there. And last but not least, if the conjugate acid of a weak base, conjugate base of a weak acid, then we're just going to look at the Ka and Kb values. Whichever one is higher, it associates more, is the one that we're going to look at. And the example given here is aluminum sulfate. Now, there are a couple of things that we can sort of use to make qualitative predictions, or make predictions without having to do the math. If the Ka is greater than the Kb, then we know that the pH is going to be acidic. It's going to be less than 7. If the Kb is greater than the Ka value, that means we know that the overall thing is going to be basic. And if Ka is equal to Kb, then we know that it's going to be neutral. So when we're figuring out these values, this is going to help us to determine which direction the reaction is going to go. Is it going to be acidic? Is it going to be basic? Now, let's take a look at the values that we have. It wants us to calculate the Kb values for the acetate ion and for the cyanide ion. Well, the way that we're going to do that is we're actually just going to continue to use the relationship we know. Kw equals Ka times Kb. I know Ka and I know Kw. So I'm going to divide both of these values. So I'm going to say 1.0 times 10 to the negative 14 divided by my Ka. This is going to be for my acetate ion, divided by 1.8 times 10 to the negative 5 once I plug this in, this gives me 5.6 times 10 to the negative 10. And for HCN, I'm going to do the same. 1.0 times 10 to the negative 14 divided by 6.2 times 10 to the negative 10, which is going to give me a value of 1.6 times 10 to the negative 5. We can use this value again to determine acidic or basic. In the case of what we have for the acetate ion, the Ka value is higher than that of the Kb, so this would force it to be acidic, slightly acidic, where it's vice versa. It's the other way for the cyanide ion. If I look at the cyanide ion, the Ka value is much smaller, meaning that it's going to be slightly basic on the other side. Now, if you wanted to go ahead and take the time to look at this, we want to arrange these from lowest to highest pH. A couple of things that are going to help you out with this. The lowest pH is going to be your strongest acid. So, in case of what we have here, we have HBr is our only strong acid. So, HBr. Then where do we go from there? Well, do we have any weak? Yes, we do. We have HF, and we also have HCN. Well, we'd have to look at the Ka values in order to really determine and go from here. Now, we're going to go ahead and take some time, and I'll actually write them out for you. And you'll be able to look at your chart and to determine where these actually fall. Again, the key here is to look at the Ka values. This being the strongest acid, I'm going to put Sa. This NaCl, we said is going to be neutral, all the way to sodium hydroxide, which is our strong base. And looking at these, we can actually determine how these salts will play out in the overall reaction. Okay? Now, consider the reaction, or consider a 0.3 molar solution of sodium fluoride. The Ka is 7.2 times 10 to the negative 4. The question is, what are the major species? Well, let's look at the reaction. That means I'm going to end up with F minus plus H2O is going to yield HF plus OH minus. Now, how likely is this to form? That's the question. We're actually looking at sodium ions being present, but we know that these are going to be neutral. We have our fluoride ion, which we had here, and our water. We're not going to form much of these two, so we're not going to be as concerned with them. Now, why isn't NaF considered a major species? Because it doesn't form again. We know that all sodium ions, or all group 1 atoms, ions, are going to remain soluble in solution, so we don't have to worry about it. So, possibilities for dominant reactions. Let's look at our choices. And we actually already talked about this a little bit, so just a little bit of a recap. Well, since we know that sodium is going to remain in solution, we can actually cut these two out. That leaves these two. And then we have to determine which one is actually going to control our pH. Looking at the values that we have, we can actually determine, that it's actually going to be here. So what is our equilibrium constant going to be, or our expression? We're going to have HF over, times OH negative over F minus, fluoride ion. Now, let's take a look at another example. We're going to calculate the pH of a 0.75 molar aqueous NaCN, or sodium cyanide solution. It gives us a Ka value of 6.2 times 10 to the negative 10. So, let's get started. What's our major species? Like we talked about before, sodium, we have our cyanide ion, and we have water. Now, this one isn't going to be a major species again. Doesn't form anything in solution. So, what are our choices? Well, both of these are gone because sodium remains soluble in water. Let's cut it down. which of the two is going to win the day? Well, we looked at the values that we had. It's either the decomposition of the water or it's our cyanide ion. And it's actually going to come out to be our cyanide ion based on the values that we have for the Ka. We just had it in front of us, 6.2 times 10 to the negative 10 is still greater than that of 1.0 times 10 to the negative 14. So, ice table, here we come. Initial concentration is 0.75. We know that this remains constant. We have a Kb value, or we can find our Kb value by doing just what we did before. Kw equals Ka times Kb. We divide both sides by Ka, and we come out with a Kb value of this. So, how do we solve? We're going to go x squared over 0.75 minus x, 1.6 times 10 to the negative 5, x. Of course, going through this, I'm speeding through parts of it, so I do apologize. You're going to end up with x equals 2.15 times 10 to the negative 5th, and we can use that to actually solve and find the pH. I'm sorry. Now, that will give us our hydroxide ion concentration. We plug that in, and again, it's just a reviewing of the same concept. If I have my hydroxide ion concentration, I can find my pOH and then find my pH from that. I'm going to come out with a pH of 11.54. Now, I want you to go back and review this a little bit. Take your time and make sure that you understand what's going on, at least the basics. If you can pull the basics, we can work with that and sort of build for the rest of the unit. Have a good evening. I'll see you tomorrow in class. Signing off.